When we combine our understanding of thermodynamics and kinetics, we will be able to analyze the energy changes that occur during the reaction. And so to illustrate this, we could look at an energy of a system, and we plot that in a y-coordinate, versus reaction progress. So versus how long reaction, how long along its course reaction went. Right? And if we start with a set of two reactants, A plus B, then we mentioned that the energy initially needs to increase so that we get over this activation energy, A. And then once we do that, we're able to get into the next well, which is deeper, where we have our product C and D. And this is why this reaction goes, because products are more stable than reactants, and they're more stable by a value of delta H0 of the reaction. Okay? And now the points of interest in this reaction energy diagram are clearly the starting materials and the products, but also this point, which is the maximum of this curve. And clearly, because energy translates into stability, this is the most unstable point along the reaction coordinate. Most unstable structure. This structure is called the transition state. And is often denoted by a double dagger symbol. Now the transition state is very different from an intermediate. Intermediates are structures which are stable, just not as stable as reactants or products, so they quickly transform into other structures. Transition state is by definition the least stable, the most unstable state of a system, and so it cannot be isolated, and pretty much anything that happens to it decomposes. Any single bond vibration or anything will take it into either back into the reactant or into products. And the transition state structure is important in analysis of the reactions, because bonds in transition states are half broken and half formed. And we can, in our example of chlorination of methane, we can look at this transition state where the chlorine abstracts the hydrogen from methane, but in the transition state itself, this bond is half broken and this bond is half formed, resulting in something that looks like that, and then finally this collapses into our product. HCl. Okay? And so the structure of transition state is very difficult to observe experimentally, but it's very important because by looking at the changes which happen in transition state, we'll perhaps be able to influence the course of the reaction. One of the most important aspects of this control of the transition state is catalysis. And so if we redraw this structure in very simple terms, what will catalysis do is lower the energy of the transition state. So this full line will be the uncatalyzed reaction, and whereas this line will be the catalyzed reaction. And so by sort of targeting specifically the structure of the transition state, this is able to lower its energy and hence lower the activation energy, thus speeding up the reaction. So this is just an illustration of how relevant the structure of transition state is in pretty much any discussion of chemical chemistry. With this, we will finish today's lecture. As you've seen, it's been a combination of study of one actual real reaction, the chlorination of methane, and application of theoretical concepts of thermodynamics and kinetics. We will speak a little bit more about kinetics the next time, and then we will return now with this strengthened understanding to the chlorination of methane in other alkenes. Thank you.